Let's talk about how our resistor, inductor, and capacitor respond to our AC waveform. Up until now, you're probably familiar with the DC voltage source, and here is our AC voltage source circuit symbol. Notice it looks like a sinusoidal waveform there. And remember, the sinusoidal waveform has certain properties that we talked about before. So here we have some peak voltage. Here would be the negative peak voltage. Between the two, we have the peak-to-peak voltage, and the peak-to-peak voltage is 2 times the peak voltage. Looking at the let's look at the horizontal axis here. I'll leave that there. Looking at the horizontal axis for one complete cycle, we call that the period, the time it takes to complete one cycle, and the period is 1 over the frequency. These are some properties you'll need to keep in mind as we talk about the effect of applying this voltage waveform to a resistor or an inductor or a capacitor. So let's look at our resistor first. Here we have the voltage applied to our waveform, to our resistor, and here we have the resulting current. And notice that V and I are in phase, as you learned previously. That means that they cross the x-axis at exactly the same points, and they have their maximums and their minimums at the same point as well. In this case, the portion of the sinusoidal equation that shows the shape, the sine 200t in this case, that stays exactly the same. We just need to find the peak current. We just need to find the peak current here. So we can use Ohm's law to do that, just like if we were looking at a DC circuit. So we have I peak is going to be V peak divided by R. So I've got 150 volts peak voltage divided by my 3 ohms of resistance. So that means we have 50 amperes of current as our peak current. Okay, so that means if this is 150 volts, this would be 50 amps if R is equal to 3 ohms. Okay, so if I were to write the equation, the sinusoidal equation, that would be 50 sine omega t, and that's going to be exactly the same that we have in our equation here. Since they are in phase, that does not change the phase shift either. So in this case, theta v would equal theta I. Let's work on a second problem. At any time during this video, if you would like, you can pause the video and work through the problem yourself, and then restart the video at that point and find out if we get to the same place. So let's look at number 2. So for number 2, we're looking for voltage given current. So in this case, again, we can find the peak voltage by now multiplying the peak current by resistance. Remember, Ohm's law still applies in AC. So we've got 25 milliamps of current. That's our peak current times 1.5 kiloohms of resistance. So we have 37.5 volts there. Since this is a resistor, that means that the phase shift of my voltage equals the phase shift of my current. So now all I have to do is write my equation for my V of t. So we have 37.5 volts sine omega t. That's going to stay the same. And since theta v equals theta I, this also stays the same. And there's the equation for the sinusoidal voltage. If that's the current that we applied to this resistor. Okay. So resistors are simple enough because really the frequency or the change in voltage doesn't really affect them. We can use Ohm's law at any point in time and get the peak voltage from the peak current or vice versa. Now for the inductor or the capacitor, remember for the inductor, the current doesn't change instantaneously. Okay, that means that just because I change the voltage in the circuit, that doesn't mean that the current's going to change instantaneously. Okay, so we're going to have to take into account the frequency of the signal that we're applying and the inductor value in order to determine how this is going to react to our AC waveform. And the way we do that is something we call reactance. Okay, we have to find the inductive reactance, and we're going to call that X sub L. And it's measured in ohms. So we're going to be able to use that in our Ohm's law equation when we find the reactance. We're going to use that just like we would resistance. And how we find that is by multiplying 2 pi f times the inductor value. And remember that 2 pi f is equal to omega, or our angular frequency. Okay, so we could use x sub L equals omega times L, or x sub L equals 2 pi f times L, depending on whether or not we're given omega or we're given f, okay? Their frequency is the same whether you're talking about radians per second or hertz. They're just different by a factor of 2 pi is all. Okay, and then keep in mind that since current can't change instantaneously, our current's always going to be behind the voltage. So we see that the voltage leads the current by 90 degrees for an inductor. So what that means is our phase shift for our current is going to be 90 degrees behind the phase shift for the voltage, whatever that happens to be. So first, let's work on calculating inductive reactance here. So we're going to calculate inductive reactance for a 2 millihenry coil. That's our inductor. And we're going to calculate it for 3 different frequencies, 60 hertz, 4 kilohertz, and 50 kilohertz. So this is 3 different problems, basically, that we're going to work here. So for A, we want to find X sub L at 60 hertz. I'm just going to note that that is 60 hertz that we're looking for here. So the equation, 2 pi f times L, and we have 60 hertz and 2 millihenries. So that means our reactance of this inductor is 754 milliohms. Let's go ahead and work the problem again. This time we are going to replace the 60 hertz with a 4 kilohertz voltage across it. Again, 2 pi FL, 2 pi times 4K times 2 millihenries. And as we increase that frequency a bit, we are also increasing the reactance. It's going to react a little more strongly to a higher frequency signal. And then let's increase it once more. If you want to take a break and work this yourself first, go right ahead. We're going to increase that all the way up to 50 kilohertz. So replace the 4K with 50K. And we get 628 ohms. So as we increase the frequency, we're increasing the reactance of the inductor as well. it's going to react more strongly. It's going to limit my current more as I increase the frequency of the circuit. So it really does matter what the frequency is of our signal. Okay, so let's apply this to find the current through a 2 millihenry inductor if our voltage equation looks like this. All right. So the first thing we always want to do is make sure we have our reactance. So in this case, we're going to look for X sub L, and remember, go up a little bit and we can use either this equation or we can use this equation depending on what we're given. We're given omega in this case, that's 200 radians per second, so I'm going to use the first equation this time. We have 200 radians per second times the 2 millihenry inductance. So that means we have about 0.4 ohms of reactance here. All right, so in order to write our current equation, what do we need to know? We need to know the peak current, we need to know omega, and we need to know the phase shift, right? So to find the peak current, I'm just going to work over here, I peak. That's going to, we're just going to use Ohm's law. That's going to be V peak over the reactance because this is measured in ohms, so we can use this in Ohm's law just like we would a resistor. So if our peak voltage, which is right here, it's 150 volts, divided by our 0.4 ohms of resistance, we see that we have 375 amps of current. That's a lot, 375 amps. Omega is going to be the same whether we're talking about I or V. So that's just going to remain at 200 radians per second. And now theta I, recall that the current is lagging behind the voltage. So if we're looking for theta I, that's going to be theta V minus 90 degrees. If we take this 90 here and we subtract it from both sides, that's the equation we get. So it's going to be, so theta I is theta V minus 90 degrees. So theta V in this case is 0. Let me clear that up a little bit. Which is just a negative 90 degrees. Okay, so negative 90 degrees. So now we have everything we need to write our equation. So I'm going to write this right here. I of t is 375 amps sine 200t minus 90 degrees. Okay, so there is your equation for current. Let's try this again. This time we're given current right here and plus 25 degrees, and we're looking for the voltage across a 2 millihenry inductor again. So we're taking pretty much the same steps here. We're going to look for X sub L, and I'm using the same equation because we have omega. So that would be 62,831 radians per second times our inductance, 2 millihenries. So that means we have about 125 and 2/3 ohms, right about there. So if we're looking for our V peak, it's going to be I peak times X sub L. And I peak we get straight from the equation, the 25 milliamps times X sub L. And that gives us 3.14 volts and that's peak voltage. Omega V is equal to omega I, so I don't really need to do anything there. That's just going to be 62,831 radians per second still. And the theta V, remember the voltage is going to lead the current by 90 degrees. So I'm just going to add 90 degrees to my theta I, which in this case is a positive 25. There's the positive sign over there. So 25 plus 90 degrees equals 115 degrees. Once I have this information, and I have this, and I have my peak voltage, I can write my equation. V of t equals 3.14 sine 62,831 radians per second. I'm just going to write t plus 115 degrees. Okay, we're going to pick up at the, we're going to talk about the capacitance in the next video. So we'll pick up with the next video.